No, this isn't working. Good morning, everybody. Hope you can hear me well. And thank you for joining our webinar, where I'll be talking about 7 lessons learned from dust explosions. I'm glad that you can join us. Hopefully you'll find something useful out of the next hour. Can you hear me now? Can you hear me now? Can you hear me now? Am I back now? What do we do? Someone said, I'm getting questions saying they can hear me fine. Good morning. Can we just check, please, that people can hear me fine? If you just type in the question, yes or whatever, into the question box. Okay, everybody seems to be able to hear me. Well, good morning. My name's Andy Fowler. I'm Technical and Operations Director at Sigma-HSE. And thank you very much for joining us for the next hour or so on this webinar, where I'll be discussing lessons learned from dust explosions. Please, if you've got any questions whilst I'm talking, please put them into the question log, and we'll pick those up as we go along. Just to give you a bit of background from me, as I say, I'm Technical and Operations Director of Sigma-HSE, housed in our headquarters in the UK in Winchester. Prior to joining Sigma, I've worked in consultancy and process safety management consultancy for the past dozen or so years, and prior to that 17 years in the health and safety executive as a process specialist, inspector and risk assessor. So I should know something about this topic. So let's start off by just explaining something about Sigma just in the first couple of minutes. A group of companies, you can see from there, we're headquartered in the UK, got offices in India and in the United States, where we provide process safety consultancy, and we also have the luxury of having testing laboratories in these locations as well. So we're able to undertake the full gambit of industrial fire and explosion hazard testing requirements and chemical reaction hazard testing requirements as well. So you can see we're a team of process safety consultants and laboratory people, experience across a very wide range of sectors, and we've got the resources of the laboratory. And I think that's enough for the selling job to start with. Now let's just look at, the title is 7 lessons learned from recent dust explosions, but really we could easily get rid of the word recent, because dust explosions occur quite often globally, dozens each year really, and it's fair to say that they've been happening for centuries now, and the lessons learned really haven't changed, so we've got to really caveat this this presentation by asking the question, why are we not learning? Because the technology's out there and the knowledge is out there, but somehow we're not using it. We're not aware of it. We're not really learning from it, which isn't surprising, because I think, in my opinion, human beings aren't necessarily that good at learning, particularly from learning from incidents from other people. We do our best, but because of the rigors of the business environment that we're in these days, it's easy to forget about some of these things. So what are my 7 learnings then from trying to stop having these dust explosions? And the first lesson, I think, lies fairly and squarely with knowledge and understanding. Do we have the knowledge? Can we use that knowledge to understand what it is we're playing with within our process industries? And there's a large element of this, of familiarity breeds contempt. Most of us will have been on operating sites handling combustible powders or gases and vapors that are flammable. And we've been doing that for years, and we've been doing it without event or only minor events. So, of course, we can very easily fall into the trap of thinking we're all in control because nothing's happening. But there is an element of we don't know what we don't know. And you've got to raise that question then, well, why don't we know? And you know, these issues, fires and explosions and what can lead to these sorts of events is very well understood in the chemical manufacturing sector and in major hazard companies, you know, storing large amounts of LPG and this sort of thing. We seem to understand there, we've got the expertise within the businesses, a lot more process engineers and chemical engineers where this is bread and butter as part of their competence. But when we're dealing with combustible dusts, powders that can burst into flame or explode, we start going into lots of other sectors. For example, food manufacturing, metal processing industries, yeah, as well as all the traditional pharmaceutical warehousing and everything else. And very often, you know, it's without that knowledge. We don't expect fires and explosions to happen with foodstuffs, but many, many dust explosions have occurred with foodstuffs. And the industry in food manufacturing isn't as heavily loaded with process engineers and chemical engineers who understand these sorts of things. But perhaps that's a problem. Let me give you an example. I remember 20 years ago now, investigating a coal dust explosion at the coal-fired power station. And in a coal-powered power station, you generally load coal into silos, and then from these silos, you transfer solid coal into a mill, and that mill's job is to reduce the particle size of the coal for feeding into the burning systems to generate the power and the heat and the steam and everything else. But at silo design, where coal's concerned, they can get things called coal hang-ups, which result in rat holes, which basically means that instead of coal falling into the top of the mill, we end up with just a space. The coal doesn't fall down. And because the mill's operating at positive pressure, we can end up with coal dust created during the milling operation, taking the path of least resistance, coming back out into the silos, which are all located internally and generally quite high up, perhaps 100 feet up within a building. So that coal dust then deposits itself on all the ledges and the RSJs around the place and sits there quite nicely. But these rat holes is a big problem for the industry. Comes back to a root cause of silo design, basically. But in this case, the company decided, well, we could have a new way of getting rid of these rat holes if we simply drilled through the silo a core into the coal, stick a couple of sticks of dynamite up into that hole and set the explosion off, then that shock wave will cause the coal to break up, fall down, and then the rat hole disappears. Okay, now in this case, it didn't go through management of change, and they tried this and they got explosive engineers in to do the job. And when I visited, all the silos in the building had plugged holes in them where they'd drilled through the silo. So they've done this operation a number of times, okay, without event. But on this case, I think what happened was when they drilled through the silo and into the coal, they also drilled all the way through the coal into open space effectively. So once they then ignited the dynamite, that allowed the shock wave to pass into the building as a whole, which raised all the dust deposits lying around within the silo building to cause a secondary dust explosion. It raised all this dust. We had an obvious ignition source, so there was a rather large explosion. And that got rid of about 200 square meters of cladding from the building, which showered down onto contractor porter cabins and so on about 100 feet below. So nobody was injured because, of course, it cleared the place of personnel or whatever. When it went to court, the defence of the explosive engineers was that they didn't realise that coal was a combustible dust. Okay? And this is part of the problem. Most sane people, when you think about it, well, what do we use coal for? We burn it. Most sane people, I would argue, would state that coal is definitely combustible and therefore the dust will be combustible, but it wasn't picked up. So there are many dusts out there which don't come with a hazard label telling you that they are combustible. So many of your food feedstocks and things like that won't be labelled as hazardous under any classification and labelling requirements under the legislation. But of course, there will be an MSDS associated with them, a material safety data sheet, which should give you that information, really, should alert you to it. But pick up many material safety data sheets and have a read of them. And very often, all it really tells you is something like the solid, the dust may undergo combustion. Okay, how the hell do you design a process based on that sort of information? There's a lot more understanding needed and knowledge to be able to design your processes to deal with potential fires and explosions involving these combustible dusts. So combustible dusts, you know, lots of things can be combustible. And with our processes, we need to make sure that we don't generate that the opportunity for an ignition of a dust cloud. Okay, and many bits of our process will deliberately generate a dust cloud. And it's pretty easy to generate a dust cloud. So that knowledge and understanding will not really help because we don't get a label on the can. Things are changing though. There's some new EU regulations coming out which are asking for further detail on this sort of information. That if your material is capable of combustion, it wants some more robust data to be provided to you so you can at least start the design, recognise that these sorts of events could happen and start feeding that knowledge into your process design. So hopefully over the next year or two, we'll see more information being placed into material safety data sheets that at least gives us the first bat at this knowledge and understanding. So the second lesson I'd like to talk about is just really basic understanding of the fire triangle and just what is a fire and an explosion. And really it's down to the simple thing of the fire triangle. Most of us know that for something to burst into flame, we need a fuel of some sort, we need some air or oxygen, and we need an ignition source. And if we can break that triangle by not having one of those steps present, either not having the fuel because we're using material that isn't capable of combustion, or we reduce the amount of air by operating under vacuum or inert systems or things, or if we can eliminate ignition sources, potential ignition sources, we won't get that reaction. It is, after all, combustion is simply a chemical reaction. And for for a simple, you know, CHO compound, as I've drawn up here, it's a simple reaction where we take a fuel with oxygen and we create CO2 and water vapor. Okay, it's as simple as that. And it's an exothermic reaction. So just like any reaction, for it to go forward, it's exothermic. So the energy of the products that we start with, the fuel and oxygen, is less than the energy of the products of combustion, but there'll generally be some activation energy. We've got to put sufficient energy in to kick this reaction off. But essentially what this is telling us is that this is just a basic chemical reaction. There's nothing fancy about it. It's an exothermic reaction. It results in flame. And that's, you know, it's a gas vapor gas phase reaction. And solids are no different, really. Because it's a gas phase reaction, obviously with solids, we've got to have a reaction with the surface of the solid. And of course, this is where particle size distribution is important, because it's the surface area to volume relationship which will essentially determine the thermodynamics and the kinetics of the reaction that occurs. Okay, so it's as simple as that. So particle size distribution is important. You know, and generally, if we think about it, we understand this. You know, if I take an iron bar, that is not a combustible metal. It's very difficult to get a combustible, to get a bar of iron that bursts into flame. But if I start generating iron filings, hopefully you can remember from school that, you know, iron filings, small pieces of iron, if we then pour those over a flame, we'll get some ignition. And then if I grind it even further to a very fine dust, then the iron dust becomes essentially pyrophoric. Open the tin and it will ignite. And it's all because of the particle size is there. This surface reaction is there in sufficient quantity to be able to generate the reaction, and off we go. So essentially, if we think about it, because we're looking at the chemistry of the situation, anything that is not fully oxidized potentially can be combustible. Okay, and the easier it is for the material to be able to react with the oxygen, so from a solids point of view, that's the particle size distribution, the easier that reaction can be kicked off. So unless we've got something that is inert to combustion, because it's fully oxidized, because it's an inorganic material, something like, you know, chalk or salt, sodium chloride, these are not capable of combustion. But most other organic materials that aren't fully oxidized will be capable of combustion. It's just a question of, can it happen on our process? So we need to understand that a bit more. Okay. So the third lesson then comes with, well, I'm okay, but I've got to have this mixture of my combustible dust in air. I've got to produce a flammable atmosphere, a dust cloud, if you like. And all that means is this flammable or explosible atmosphere is simply the mixture of powder and dust in air within certain concentrations. So we've got to have, you know, the right proportion of fuel and oxygen present to allow the reaction to go ahead. If there's too much fuel, then it's too rich to burn. If there's too little fuel, too much air, it's too lean to burn, so we won't get combustion. We need to be within certain concentration ranges. You know? But, you know, so the question we've got to ask ourselves is, on our process, where can we produce clouds of dust? Where can we produce these flammable atmospheres on our plant? Because without that knowledge of knowing where they can be produced within our plant, it's a bit difficult to then put in place the measures to prevent that from happening, to stop that ignition. So of course, where can flammable atmospheres occur? Really, it's simply down to when we're moving powders, when we're transporting powders, mixing powders, conveying it, whether it's pneumatic or screw conveying or whatever, filling, emptying operations, etc. All of these are capable of creating a potential dust atmosphere, which if we've got a source of ignition, will kick off that reaction and we'll have a fire or an explosion. Okay, but of course, you've also got to remember, coming on to lesson number 4, is that when we move powders, or indeed if we move vapours or liquids, we're creating electrostatic charge. So, you know, whilst we're doing these movement operations, we are in fact potentially creating a means of igniting that cloud as well. Okay, so that full understanding of where we can get these explosive atmospheres is really important. We've got to look at the tasks that we're doing. I remember another incident I investigated many years ago, where a chap was killed, and what they were doing, it was in an aluminium smelting operation, and so they were simply manufacturing alloys of aluminium. So they had an aluminium furnace with molten aluminium with it, and then they were then adding various other small amounts of metals and so on to create the alloy that they were after. And in this case, they were wanting to add magnesium into the melt. Now, what their normal operation was to buy ingots of magnesium and simply throw them into the furnace containing the molten aluminium. Obviously, an ingot of magnesium, not a problem, but no possibility of creating a dust cloud there. The ingot will simply fall through the molten aluminium or sit on the top and melt and be incorporated into the whole molten mass. But there was an opportunity to save a bit of money. They found that they could buy waste cuttings from other manufacturing operations of magnesium swarf and the like. And they thought, well, we can add that in as well. And that's what they did. So if you can picture the situation, they tipped out cans of magnesium swarf that hadn't been treated in any way. So it was powdery in nature as well as having swarf. It still had cutting oils on the surface of the material. And the chap's job was simply to shovel this magnesium swarf and dust into the furnace opening. So they had a pile of magnesium outside the furnace door, opened the furnace door and started shoveling in magnesium swarf. And as you can imagine, by shoveling in swarf, just throwing it in, a flammable cloud was developed. There's a good ignition source when you're operating at hundreds of degrees C in a furnace. So there was a little dust explosion, if you like. Out of the furnace opening came a fireball that ignited the magnesium that was just piled outside the door, and all hell was let loose basically, and the person was killed. What was annoying was in court it came about that they did similar operations with aluminium, so they could add aluminium cuttings. But they had equipment on site to take this raw material as such, to wash it to get rid of cutting oils, to sieve it to get rid of powder, and to dry it to get rid of moisture before they added it into the kiln. And they didn't reach the conclusion that they should do something similar for magnesium. The only step in that that's more difficult with magnesium is you can't dry magnesium swarf with a direct flame. You'd have to use an indirect means of removing the moisture from the magnesium swarf. But in some respects that they understood the hazards that were involved, but didn't transfer that understanding when dealing with a new type of material. Obviously, the other way of breaking the fire triangle is to remove ignition sources. And, you know, the DSEA legislation in the UK is quite heavy on removing the potential ignition sources, and the standards and that associated with those regulations, BS 60079 and so on, states the potential of 13 ignition sources, and these are all highlighted here, many of which are common, like hot surfaces and flames and sparks and electrostatic and electrical currents and things, but all the rest are associated essentially with electromagnetic radiation. It's just another form of energy. So you can see when we're looking at trying to prevent ignition of flammable dust clouds, there are a lot of ignition sources we need to cater for, okay? But we need to. As a process safety professional, we're brought up with elimination of ignition sources is pretty low down on the pecking order of the things we should do to prevent ignitions. It's very difficult to be able to eliminate all potential sources of ignition all of the time, okay? And although we can do our best and we can comply with ATEX, so we can have properly certified ATEX equipment that shouldn't act as a source of ignition for all our mechanical and electrical equipment, we can earth our equipment to make sure that we can discharge electrostatic hazards and so on. You know, we can still have the case of malfunctioning equipment. So we've got the equipment, but we don't look after it well enough, or it was incorrectly designed in the first place. And we assume, in many cases, assume that our equipment is correctly earthed and bonded. So checks should be taken every time we do some maintenance on the kit, we break into a line or whatever, that in fact we have got earth continuity. Otherwise the whole thing breaks. And you know, it is, although earthing is something that's pretty simple to deal with, you only have to, you know, if you buy one of these kits that are quite common, for example, during tanker offloading operations, you can have a bit of kit where you stick a clamp onto your road tanker to make sure that the earth tankers and so on. But you get a positive indication that you've got earth from that. A light comes on to say that you've got earth. And when you buy these systems, it's quite staggering how often you have to actually move that clamp around to get your positive indication of earth. Yeah. Now, if you haven't got that sort of monitoring equipment and all you're doing is sticking an earthing clamp on, a good proportion of the time you think you've got earthing, but you haven't necessarily got it. May or may not be a problem, will depend very much on the electrical properties of the material. Obviously, things that are high resistive or insulating, charge can build up, and that can become a problem more than a conductive material, and so on and so forth. But you know, identifying all your ignition sources is possible. Preventing them from becoming a potential source of ignition can be difficult most of the time. We do our best, but you know, we live in a world of risk. We live in a world of probability, so these things can still happen. Lesson number 5, when we look at incidents that have occurred, is housekeeping. Keeping these dusts within the equipment where they're meant to be, primarily, not having leaky equipment, not resulting in dust powders coming out and settling out on the roof rafters and the light fittings and so on and so forth. Because if that occurs, if we've got very leaky equipment, we can end up with what's called secondary dust explosions, which has resulted in some of the largest industrial explosion events. It's these secondary dust explosions that tend to wipe a factory out, unfortunately. And the next set of screenshots just sort of indicate that. So, you know, when we're handling powders, we tend to have some powder collection units, and it's very typical for those to have venting as the basis of safety on there. So if there is an ignition in your dust collection system, and after all, that's where we're collecting the really fine dust, the dust with the greatest potential to ignite, out from that vent, if it operates, will come a ball of fire and a little bit of pressure. Okay, so if we assume we have an ignition within that piece of kit, then that will create a shock wave within the building. That will start knocking the dust, the dust deposits that are lying around the factory on the roof rafters and the lighting units and on top of the electric motors and so on. That's then generating a large dust cloud, a very large dust cloud, might be the whole building. Of course, we've got a large ignition source there, just sitting waiting, which of course will ignite that dust explosion, and we end up with a very catastrophic explosion that starts wiping buildings out and knocking floors down and knocking the walls down so the floors collapse and so on and so forth. And we end up having a catastrophic event that has in the past resulted in many fatalities. Okay, so it really is important that we do have housekeeping. We don't allow these dust deposits to build up. And it's interesting, I think, in my experience of going round the whole plethora of different types of processing operations handling combustible dust, it seems to be very housekeeping seems to be very dependent on how valuable the product is that you're dealing with. If it's a very expensive pharmaceutical ingredient or something like that, you'll find very few leaks in their conveyance equipment and the way they handle the powders. But if it's a very low cost material, especially in something like the food industry or the animal feedstuff industry and so on, or wood operations dealing with sawdust and this, it's not a very valuable product, and we tend to see dust layers all over the place. So, you know, we can do the job. We can make sure that we have leak-tight equipment, the technology's out there. We can ensure that we have cleaning routines within our operations to collect up this dust if we do get the odd leak or whatever. But it is really important, because these are the things that result in the largest types of dust explosion. Lesson number 6 comes on to, again, something that makes the largest explosions a lot worse than the initial one, and that's propagation of flame or pressure within our processing plant. So if you can imagine, if we have, you know, in all our processes, we've got vessels and silos and things linked by conveying systems, ductwork, and so on and so forth. If we have an ignition within a pipe, the flame and the pressure front will take the path of least resistance, either upstream or downstream, and it'll trundle its way pretty quickly into adjacent pieces of equipment that may contain a lot more dust, and so on and so forth. So we can get a series of explosions going along from what is a relatively small event in the first place, but goes upstream and downstream and creates bigger and bigger explosions as we go upstream and downstream. We can get a phenomenon known as pressure piling, which is essentially accelerating the flame front, and it's the acceleration of flame front that results in pressure. If you think about it, you know, the difference between a flash fire and a explosion is simply, with an explosion, there is means of accelerating that flame. It's either due to containment, or which leads to flames and that mixing and creating increased surface area of the flame, which is accelerating the flame, or congestion. So flame comes across obstacles that it can't get through, so it accelerates past them. And flame acceleration results in a force. It's simply Newton's second law of motion. Force equals mass times acceleration. If I accelerate a mass of flame, I start generating a force, and that force is pressure. And that's when we start blowing things apart and sending missiles around the place, which of course can do a lot more damage than a little simple flash fire, which is just a thermal event, relatively slow in nature, slow enough that most flash fires you can run away from. Okay, once we start accelerating that flame, we start getting into potential. Therefore, to stop that, we've got to have measures installed within our process to stop that flow of flame or pressure going from the source into other processing vessels. And that can be simple things like rotary valves, and I state here simple things, but correctly designed rotary valves capable of doing the job, quick acting valves, suppression systems, and so on. So these become part of what's known as our basis of safety. Okay, so there's means of doing it. These are when we've been talking about not trying to prevent a flammable atmosphere or trying to prevent ignition. Those are prevention devices, but we've also got to take account of if we do get an ignition, then we've got to protect ourselves against it, which is where we're talking about things like venting or suppression systems or containment of that pressure within a system or whatever, all of which requires some form of isolating items of equipment from each other via these sorts of means. And the big explosions that have occurred throughout time is because we haven't had those measures installed. So the explosion has ripped throughout the whole process, resulting in a lot larger event. And the seventh lesson is management of change. You know, not changing our processes, not considering in a robust and systematic way changes that we make to processes, because all processes change. It's a fact of life. We like to tinker, we like to make things better. Sometimes if we don't think about management of change in a very robust and systematic way, the number of times where this has been a root cause of fires and explosions, because we haven't thought about it robustly enough and put in place measures to deal with the hazards that we're dealing with. So management of change, you know, where you've got to ask yourself on your process, yes, it's maybe been there for 30 years, but how different is it? Are we sure nothing's changed? Is the equipment the same as the design intent? Is the process the same? Are the tasks that we do and the substances, are we now dealing with finer solids than we were initially, and so on and so forth? Or drier substances, where before we had more moist substances, all of which, you know, added moisture, larger particle size will all reduce the probability of dust explosions from occurring. So those are my 7 lessons, which I hope you found useful, and things to discuss and think about on your own plant. But, you know, dust explosions continue to occur. They've done it for centuries. Yeah. And you can bet your bottom dollar the next one that happens in the next month or two, it'll be one of these 7 lessons which we haven't had control of that has resulted in it. There is very little new to learn from fire and explosion incidents. The last one that was considered unusual was the Buncefield event, which wasn't dust, it was petrol vapor. But, you know, once that incident occurred, it was stated, well, we didn't expect that to happen. This is a new mechanism. It really isn't a new mechanism when we've looked at it, and we'd had similar events in the past before Buncefield. We just hadn't picked up and took the learning and developed it further. So there really is very little that's new. Now, the problem with dust, of course, is because it's very dependent upon the nature of the dust and its particle size distribution, the way in which we have to, the propensity for it bursting into flame and combusting, resulting in dust explosion or fire, can't be calculated. What's gone wrong? I've lost. Everything's still okay. So the way in which we deal with it, as I said before, is we deal with it from two ways. We deal with it, we're trying to prevent the explosion, which is done by either removing ignition sources or removing flammable atmospheres, or explosion protection, which is dealing with the ignited event through venting, suppression, or containment. Those are the three ways of doing this. But it requires knowledge of the substances and test data for each of these things to be designed appropriately to make sure that they are effective. A vent that is not large enough on a vessel will not stop the vessel from blowing up. A suppression system that is not quick enough acting will not prevent the explosion from becoming a lot bigger than it needs to be. Okay, and so we need some raw data, and we can't calculate this raw data because of the nature of combustible dust. We've got to be able to test it and to get these parameters. Okay, so as I've said before, explosion prevention, remove the fuel. Don't work with combustible dust, work below the lower explosive limits. So we haven't got sufficient concentration of fuel in air, which might be because we're only working with large particle size stuff or this sort of thing. Remove the oxidant using gases, work under vacuum. Remove all the ignition sources. But whatever we do has got to be designed appropriately. So let's just have a look at the sorts of tests that give us this information. The first test is simply what we know as a go, no-go screening test. You can see the apparatus here in the diagram where we generate a flammable cloud and put a large ignition source across that flammable cloud, and we see if it goes bang or it doesn't go bang. If it goes bang, and we then classify it as a combustible dust, it's a group A dust. If it doesn't, it's non-combustible. It's as simple as that. It's a group B test. So that tells us whether the material we are dealing with, and we'll generally do this over a number of particle size distributions, and so you can link that with the way in which you handle and your processes, and whether your processes are capable of reducing particle size or whatever, so you can get a handle on whether or not the material is combustible or not. If it's not combustible, the problem goes away. If it's combustible, we need further data. To break that triangle, we can limit the oxygen concentration. So again, we all know that on this earth, with 21% oxygen present or whatever, we know things burst into flame. We also know that if we reduce that oxygen level, certain things will not explode. If we take it down to its limit and work under full vacuum, nothing will explode because there's no oxygen there. The problem is the amount of oxygen necessary for that chemical reaction to be kicked off differs dependent upon the substance. So we've got to test it. So of course there's a standard test where we can determine the allowable concentration of oxygen, and you can see some typical values here. So for organic pigment, rye flour, if we work below, get our oxygen concentration below 12 or 13%, we've got a basis of safety there. If we're dealing with aluminium, we need to get down below 5% oxygen to make the process safe. If we can achieve that, and we can achieve that robustly and systematically, we've eliminated the potential for an explosion, because we've eliminated that generation of the flammable cloud. We haven't got that mixture of the dust with sufficient oxygen to kick that reaction off. Also, of course, is minimum explosive concentration of the dust. So this is the minimum quantity of dust dispersed in air that will form a flammable atmosphere. This test is measured in what's called a 20-litre sphere that I'll explain to you in a little while. It's just another bit of standardized test equipment. It's akin to the lower flammable liquid for flammable vapors, the lower flammable limit for flammable vapors and so on. If we haven't got sufficient concentration of dust, of fuel within our dust cloud, okay, it'll be too lean to burn. And you can see here, and a rule of thumb basically says your dust cloud got to be that within 2 meters, you wouldn't be able to see a 25-watt bulb through a combustible dust cloud. So it is quite an intense dust cloud that you need to have present to achieve a minimum explosible concentration. You can see for coal dust, it's of the order of 40 grams per cubic meter. Okay, it's all laid down in specific test requirements using specific test equipment to the standards, whether they're in Europe or in the USA. In terms of ignition sensitivity, the third part of the fire triangle, explosion triangle, minimum ignition energy, we've got to have sufficient energy to kick the reaction off. Okay, so the minimum ignition energy is the lowest spark energy that can ignite the optimum mixture of fuel when dispersed in air. So we generate an optimum cloud, which will generally be using the finest material that we've got. And the ignition that's used within the equipment can be developed under 2 ways. It can either be developed using a capacitive mechanism or an inductive mechanism. I won't go into the differences there, but essentially the capacitive discharge is used to look at the energy required from an electrostatic discharge that could cause ignition, and an inductive discharge from mechanical sparking. So within the same test, but by using 2 different sources of ignition, we're able to determine the ignition energy for electrostatic discharges and mechanical energy and mechanical sparks and so on. So clearly, any material, if those sparks, if the electrostatic discharge energy or the sparking energy is larger than the minimum ignition energy of the dust cloud, it will ignite. If it's not, then of course there's insufficient energy to kick that reaction off. Again, undertaken in specified, standardized equipment testing. And just now, just to show you a little video of one in action. So there's a video of the minimum ignition energy. You can see there, we generate the dust cloud, we send the spark through, we get ignition. As simple as that. Okay, but we're able to determine, put different amounts of energy through 2 different types of sources to be able to give us information on the minimum ignition energy. This sort of knowledge, you can then look at, well, can we generate sufficient energy to ignite this cloud from the mechanisms that we've got on the plant to stop these sorts of things. So you can see here, something like cocoa powder need about 100 to 300 millijoules. Aluminium or some active pharmaceutical ingredients can be very low. Okay, so for example, electrostatic discharge from human beings wandering around the place in their clothing won't generate sufficient energy to ignite a cocoa dust cloud. but definitely will an aluminium or an active pharmaceutical ingredient in many cases. You see? So we can look at the measures we employ then on the back of this sort of information. Now that's looking at energy. What we've looked at there, minimum ignition energy, is looking at the energy generated from sparks, really, whether they're electrostatic sparks or mechanical sparks. Of course, we can put energy into systems by having hot surfaces, which we all know about. So the minimum ignition temperature is the lowest surface temperature that can ignite the dust cloud. Okay, so it's equivalent to the auto ignition temperature for flammable vapors and gases. Okay, and this is important because if you're using certified ATEX equipment, part of that certification is what's known as a temperature classification, which is basically saying that this piece of equipment can't generate temperatures greater than this. And provided that that temperature is less than the minimum ignition temperature of any dust cloud that's present, the hot surface won't ignite that dust cloud. Okay, so we can then, choose the correct equipment to be installed according to its minimum ignition temperature. And of course, so that's ignition of a gas cloud. We can also have ignition of a dust layer, what's known as the layer ignition temperature, the lowest surface temperature that would ignite a 5mm layer of material. And you can use this, there's some little equations that we can look at the minimum ignition temperature values and the layer ignition temperatures to calculate that maximum surface temperature of equipment that feeds into your temperature classification for the equipment. So it's simply just a test where we raise the temperature up of a 5mm depth of material in a standardized test and look when it starts to ignite, the temperature at which it starts to ignite. So, all of this range of temperatures is very important. That allows us to look at the equipment that we've got and how we've constructed our processes to how we can, what's happened there? You still see the screen. Basic parameters. One of the most important ones, though, of course, is if we can ignite a dust cloud, is what's the pressure that's developed. With most vapors and gases, organic vapors and gases, the rule of thumb is we tend, if we ignite it in a contained explosion system, we'll generate about 7 or 8 bar of pressure. Again, with combustible dust, it's very dependent upon the material and the particle size distribution. So this equipment, the 20-litre sphere test, is where we essentially deliberately create a flammable atmosphere, put a source of ignition across that cloud, and then start measuring the maximum explosion pressure from the test. So what's known as Pmax. And not only do we use the Pmax value, but we also calculate the rate of pressure rise of that explosion overpressure. So how quickly that explosion overpressure is developed. And that can be altered, this dP by dt can be turned into what's known as a dust constant, the KST value of a particular dust. Obviously, if we are going to try and contain explosions, or in fact design suppression or venting arrangements to handle ignition of these sorts of dusts, this knowledge is paramount. Without this, we cannot design either vents that are suitable enough or containment systems that are suitable enough, or in fact suppression systems on how quickly they need to act. So this is fed into your basis of safety then to make sure that it's going to be effective. We've got to have this data. We can't calculate it. We've got to do it via testing. And again, as with everything, it's undertaken according to standard methodologies, which may differ slightly between countries, but essentially are identical, just given different labels. So those are the most usual dust explosion parameters. Of course, there's many other characteristics of solvents, especially around their electrical properties, that are also important. So high resistivity solids, or if you like, insulating solids, if we can generate charge, which is easy to do, because they're insulating, they will remain charged for some time. Conducting materials will lose that charge as quickly as it's developed, provided the system's earthed and so on and so forth. So the standard tests for getting to grips with this sort of thing as well. But I've just looked at the dust explosibility characteristics. So you can see here the range of KST, the rate of pressure rise, which are categorized into what's known as ST classes. So ST1 is, if you like, the weakest type of explosion. Materials at ST1 dust result in the weak type explosions, generally from things like powdered milk, sulfur, sugar. ST2s, strong explosions, cellulosics, wood flowers, PMMAs, these sorts of things. ST3s are generally quite frisky stuff generally, and our metal powders, aluminium, magnesium, anthraquinones, things like this, result in very strong explosions. You can see greater than 300 bar meter per second. That's quite a steep explosion development curve. Yeah, so it happens quickly and the pressure is high. We might be talking here getting up to about 12 bar. Okay, so quite beefy. If you're looking at containment, you're requiring some quite beefy containment systems there to be able to deal with these things. And as I've said before, I keep reiterating this, it's the particle size that has the major impact on this. So you'll find in lots of the tests that are done, they will be screened to give us deliberately the finer fractions of the materials that you use on your plant, because these will give the worst case explosion characteristics and ignition characteristics of the powder. And it's all because of this surface area to volume relationship. Generally speaking, if you can operate, if we don't have any stuff less than 500 microns, we're generally okay. It won't be a combustible dust. As we go below 500 microns and get down to the tens of microns, lots of things will explode at that sort of thing, at that sort of particle size. And don't forget, there'll be certain bits of your processing plant where you are deliberately creating fine material, your dust collectors, for example, or when you're filling and emptying and so on like that, your particle size, that fine dust will tend to find its way removed from the bulk properties of the powder. So hopefully I've given you a flavour there of the testing that's required. Just in terms of Sigma-HSE doing this in our testing laboratories, which are fully accredited testing laboratories to 17025, we've got generally worked to 5 to 7 days turnaround from receiving the sample. Fully competent people to do the job, and have worked with clients throughout the world. Now, a few questions have come in, which I'll just see if I can answer. It says also, if the NRE required what will change be will be dependent upon the concentration. Okay, and that will be measured when we do the stuff. We pull that apart because we do a range of particle size distributions and a range of concentration. Okay, which test is more sensitive or inductive? Really, there's no answer to that. To look at different phenomena. So you're in there is looking at sorts of energy that we create from mechanical sparking, and then the capacity discharge is from the electrostatic point of view. So there's no more sensitive, but generally speaking, electrostatic can be greater. The electrostatic is lower, so the capacitive MIE can be lower than the. Now then. It's not right. So somebody's raised the question here, I'll read it out. As for the explosion index test, the samples are generally milled sub 60 microns, even if this size material does not represent the fine fraction found in the process. How can I relate explosion test results on finely milled samples to material that is an order of magnitude larger in reality? For example, a mill sample could indicate ST2. What deduction do I make from this? Free the material in the plant. Well, that's a difficult decision, really, but it is a decision for you to take. And really, to feed in to make that decision, you've got to look at in your processing detail and say, well, can attrition occur in the process? Can it change under time? What control have we got onto the feedstock coming in? How, in terms of quality, is particle size distribution part of the quality description of the material and so on and so forth. So I hope that's answered. So there isn't anything. It's always best to err on the side of caution. Is this telling? I think that's it. So if you'd like to get in touch with us, you've got the details there on the last slide. You can send us an email. You can give us a call. We'll do our best to help you. I hope you found the event to be successful and interesting and worth listening to. I hope you found it enjoyable and a good way to kick off the middle of the week. And with that, I'll close down and let you all get back to earning some money for your companies. So thank you very much and speak to you again soon. Bye-bye. There's just a few there early on saying sound gone down, but they were all early, weren't they?